For my final project, I did Pass the Pig solutions using Elasticsearch. Pass the Pigs is a game created by Hasbro and incorporates concepts like expected value, risk analysis, probability, even though a child can play it. The basic goal of the game is to get to 100 points before your opponent. The game has two pigs, which a player tosses. Depending on how the pigs land, the player may accumulate points, lose all the points they accumulated during their turn and their turn ends, or pass the pigs and keep the accumulated points in their hand. There have been many articles written about statistical solutions to the game, Bayesian analysis based on unknown prior probabilities of pig outcomes, and analysis of optimal and heuristic strategies. I'll take the same data for the hand equity of each possible hand for 6,000 hands of Pass the Pig and load that data into Elasticsearch to see if the machine learning capabilities can find an optimal solution comparable to my Python dynamic programming solution. The pipeline overview and technologies used. For the collection tier, I used Elasticsearch with Python scripts in a notebook ingesting Pass the Pigs data. Elasticsearch will be ingesting data from Pass the Pigs. The storage tier, S3, to store Pass the Pigs data. The visualization tier, I will use Kibana with Elasticsearch to visualize and correlate the Pass the Pigs hand equity data. Machine learning tier, I used Elasticsearch's data regression model. Pass the Pig utilizes two pigs as dice, and the rules are simple. On a turn, one player is required to roll the two pigs. Based on the landing positions of the pigs, the player determines how many points they have accumulated during that turn. The player can then either pass the pigs to the next player and add to their point score, or roll again to add more points to their score. But should they land both pigs with a dot showing up, then they lose all the points they accumulated during the hand. The first player to cross 100 points wins. Given the varied scenarios, it's important to understand whether to roll or hold the points one has accumulated. I will develop a dynamic programming model in Python to be able to solve for optimal strategies given the number of points in the player's hand, the opponent's hand, and how many points they have accumulated during the hand to roll or stop. Then I will load the same data into Elasticsearch to find the optimal strategy utilizing machine learning models within Elasticsearch. The game logistics. Utilizing the figure on the left, I can determine the probability of each pig roll along with a joint probability from any combination of two pigs. This data is fundamental to be able to build my machine learning and dynamic programming models. For example, if you roll a razorback, you will get 5 points. If you roll a double razorback, you will get 20 points. Generation of support data. First, I need to calculate the appropriate probability distributions to understand the value of each roll. Below is the probability of the pig position for any given single roll. From here, I have to calculate the joint probability of each of the two pigs, then map out the point value for the positions from figure 1. In determining the decision variable, what I would like to know is the greatest chance I have to win given the point value I have in my hand, t, points I need to win, x, and the points my opponent needs to win, y. This permits us to determine the equity in my hand. I use the Bellman equation for my dynamic programming problem below. In figure 6, I have each possible outcome described for my dynamic programming model. Quit, pig out, gain k points, and win. Now that I know I have a recurrence for equity to describe the value of my hand, my opponent's hand, and the probabilities of each outcome for a pig roll. The value for equity assumes that my opponents are choosing similarly optimal policies from their point of view. In my Python program to generate the optimal strategy for Pass the Pigs, I've created several functions to aid the player. I have the function compute function nk, which computes the probabilities of winning in games up to n points using k iterations. This function uses compute line by line n, which computes the equity of the player's turn via my recurrence in the figure above. This function assumes that the values for the previous line are computed properly, that for all x and y in this region n, where x and y are less than n, that function x, y, t is accurate. I'm going to compute the values on the edge of this function as 3, where at least one of x and y is n, and one is at most n. I repeat calls to this function until the values settle down, making sure that the maximum change is below an error threshold. Below is the output from Find Strategy, where if I have 50 points to go to win, and 40 points for my opponent to win, I should roll again, given the point total in my current hand. First, I had to install Elasticsearch. To configure Elasticsearch in Kibana on Mac OS, I followed these steps. Install Java using Homebrew, install Elasticsearch using Homebrew, install Kibana using Homebrew, then configure Elasticsearch and Kibana using the default configurations, start Elasticsearch and Kibana, and finally load Kibana in my local web browser. Here is the running of my Elasticsearch instance. Then I need to pass the pig's hand equity data into Elasticsearch. I loaded the 6,000 records from the fast R2 data set, which contains information collected from rolling the pair of pigs found in the game Pass the Pigs 6,000 times. It's the format. A data frame with 6,000 observations on the following 6 variables. Roll number 1 to 6,000, black score numerical code for position of black pig, black position of black pig coded as a factor, pink score numerical code for position of pink pig, and pink position of pink pig coded as a factor. Then I wrote a Python script to load this data into Elasticsearch. Then I run the data regression job. So I took my data set for all of my dice rolls and correlated them to each other. This is just more of those regressions. Then I finished my correlation result, and you can see the ML model results here. I can see that my ML score prediction is around 20 for the stop first goal for a roll. And then my dynamic programming solution predicts a stop go for a roll at 50 points to be at 22 points versus Elasticsearch's ML model, which predicts the stop go should be at 19.22. In conclusion, though Pass the Pigs is a simple game, the fact that one might lose all of the accumulated points in their hand causes it to be a complex dynamic programming problem. Understanding the equity in one's hand and whether or not to continue to roll or to stop, and how that affects your potential to win is a similar problem to many other games, for example, blackjack or backgammon. And my Python model can be expanded to support those other games. If I created hand equity data in a form that can be ingested by Elasticsearch, I can generate a similar prediction within 30 minutes rather than the multiple days it took me to create the validation model in Python. But this requires me to generate data that could be trained and tested by the 3 ML models that were available to me in Elasticsearch. If I didn't have data in the format that would be easily managed by Elasticsearch, if we're not two-dimensional or not fully denormalized, I would not be able to understand the models within Elastic nor the visualizations within Kibana without transforming the data. I have yet to leverage my program against online versions of Pass the Pigs or other human opponents, but I look forward to testing out the application to prove its value and collecting additional data to perfect my ML model within Elastic. Thank you very much.